So, thirdly, is the issue of the flood of deleterious mutations pouring into the human population. So if mutation rate is too high, natural selection cannot remove the mutations as fast as they arise. So again, coming back to Kimura, the Nobel laureate. So he, in 1950, wrote the book, Our Load of Mutations. And here's what he says. It's surprising what he says. Actually, his whole paper is surprising. But here's what he says about the critical mutation rate. He was very, very concerned that we were near the tipping point where mutations, if the mutation rate goes too high, human race must degenerate, and if it continues all the way to extinction. So he was extremely concerned about this, and so he was asking, a major concern at that time was nations were using nuclear testing in the open air. So there was radiation floating throughout the atmosphere of the world. He's saying, we may be destroying the human race in the long run by doing that. So he wanted to know the tipping point. He says the upper mutation rate, the beyond which equilibrium is impossible, must be much lower than 0.5. That means half a mutation per person per generation is too high. And he goes on to say it might even be as low as 0.1, one mutation in 10 individuals every generation. Even, he says, if selection were to be given full scope. So he was a eugenicist. He would have said, let the unfits perish. Don't let them reproduce. But he's assuming intense selection. By the way, our numerical simulations, we always assume 50% our default parameters, that is half of the population of a generation. So we're doing very intense selection in our numerical simulations. Much more than Muller would have said would be reasonable. So let's look at the numbers behind Muller's estimates. So a lot of population geneticists have looked at this issue, and they've come up with an equation, and it really was not going to Crowell published the equation, but apparently Kimura was already making similar calculations, and it's apparent that Muller was doing similar calculations. But so here's a formula that tells us how much of a population must be selected eliminated, depending on U. E is a constant. U is the number of deleterious mutations per person per generation. So it can tell us how much elimination is needed, or a slightly different formulation. It tells us how many offspring per female are required to stay ahead of the bad mutations, so we can select away the bad mutations as they accumulate. For a mutation rate of 0.1, which was Muller's estimate, that requires 10% selective elimination. Now, when I say 10% selective elimination, I'm not talking about normal juvenile deaths like due to car accidents or wars or pestilence. I'm talking about where people are dying because they are distinctly inferior to the people around them. So selective elimination doesn't include all that accidental death. It has to do with fitness-based death. So this is actually this is kind of an upper limit. A lot of geneticists would say, yeah, 10% of the population being selected away is a realistic number. So that's manageable, but if the mutation rate goes to 1, it actually becomes problematic. You have to get rid of 63% of the population, and that means minimally, even after the accidental deaths, 5.4 offspring per female, so that 2 certainly can survive. Mutation rate of 2, it goes up to 14 children per female. And for mutation rate of 3, you need 40 offspring per female, not including the accidental deaths. So this is the Nachman and Crowell paper. Basically, they were measuring 175 new mutations per generation. They're off a little bit, but it doesn't matter. The genetic load associated with such a high U would be intolerable. They go on to say, for U equals 3, deleterious mutation rate of 3 per person per generation, each male would need to produce 40 offspring, as our calculations show, and this assumes all mortality is due to selection. So basically, there's a series of papers that say that. Here's one that says it's difficult to explain how human populations could have survived a high rate of deleterious mutation, where they consider a high rate of mutation anything over 1 is paradoxical to a species with a lower reproductive rate. And they go on to say, deleterious mutation rates appear to be so high in humans and our close relatives, it's doubtful that such species could survive. So the interesting thing is they're assuming that the actual mutation rate is down around 1 or 2 mutations per generation. All of the people I'm going to describe assume that 90 to 99% of the genome is junk DNA. So that's now very much in doubt. It's widely considered. It's widely recognized that there are more than 3 mutations per person per generation that are deleterious. So here's another author. The implications of mutations of this magnitude for population genetics and evolutionary theory are profound. The question of how our species accommodates such mutation rates is central to evolutionary thought. So they're saying this is a big deal. This isn't some side issue. Just looking at the mitochondrial DNA, just looking at the infinitesimally tiny part of the genome, they say we should increase our attention to the broader question of how or whether organisms can tolerate, in the sense of evolution, a genetic system with such a high mutation burden. He's just talking about mitochondrial mutations. Here's the most recent publication on this issue, a book written by Alice Kondrashov, who was here for NIH for a long time now, is teaching at Michigan State University. He just wrote a book called Crumbling Genome, and here's a few interesting things coming from his paper. Number one, he says in the average human genotype, over 100 genes are dysfunctional or missing. And he adds, and over 1,000 genes are substantially impaired. Doesn't that make you feel healthy and vigorous knowing you have carried that much genetic load? It's very, very concerning. He goes on to say a newborn human carries about 100 new de novo mutations originating in the germline, and he says about 10% of those are substantially deleterious. That's a huge thing to say. To say that 10% of the genome is functional means that you need 10 mutations per person per generation, which goes way over the top in terms of what a population can sustain. So we used this formula earlier. And basically, if with 10 mutations per person per generation, you need 44,000 offspring per female. That's not exactly reasonable. Now, Dan Brower has chided the ENCODE project at NIH for considering that perhaps a large fraction of the genome might be functional, let's say even 80%. In which case there would be 80 new mutations per person per generation. And he said he correctly realizes you need something like 10 to the 35th power of offspring per female. And he calls that bonkers. And I say that Dr. Brower is totally right, that is bonkers. But 10 to the 11th is bonkers. And 44,000 children per female is bonkers. So all these assumptions assume that their genetic degeneration is not happening. And it's clear that all those calculations are bonkers. Mutations are happening at somewhere between 10 and 80%, or some significant part of the genome is functional. And that's why people are upset about ENCODE, is because if there are a significant part of the genome that's functional, then we are experiencing rapid genetic degeneration. And so there are many lines of evidence that show this. All these paradoxes go away if we simply accept that the genome is degenerated, which is painfully obvious. Okay, so do people argue against this? They do, but it's kind of like